Stays where it either stays where it's at or it goes up. Or maybe it stays where it's at and only goes down. But the important thing is that it does not go both down and up. Like it doesn't do this. So the way that that's sort of phrased is it's either non-decreasing, the sequence is either non-decreasing and they use the phrase non-decreasing as opposed to increasing because it is allowed to stay the same. So to be non-decreasing, each term is at least as large as the last. Maybe it's larger, but it's at least as large. As a previous term. So maybe some terms are like the same as the previous terms. Maybe some of them are bigger, but if that happens, the sequence has this sort of it goes in one direction. So like the sequence 1, 2, 3, 4, 5. That's all increasing. But the sequence 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, that would also be considered monotonic because each term is at least as large as the last one. It doesn't, go up and down, so that counts as well. Or when its terms are non-increasing, meaning that meaning that it doesn't go up. Maybe it stays where it's at or it goes down, but that's all that it does. It either stays where it's at or it goes down. And all that would mean is that each term is at least as low as the previous one. So that would be a sequence like 1, 1/2, 1/4, 1/8, 1/16. That's going down. Each term is lower than the previous one, and that would be considered a monotonic sequence as well. Basically, the important thing is, to be a monotonic sequence, you can't both go up and down. You have to choose one or the other. And it's sort of this unidirectional sequence. So we'll check for the monotonicity of a couple of different sequences. We saw a couple of these sequences on Tuesday. All right, so this first sequence, a sub n. If you remember from Tuesday, that's the sequence that starts off with 2. The second term is 4. The third term is 2. The fourth term is 4, and just sort of so on and so on. Just because it's got that -1 to the power of n, that's going to alternate between -1 and +1, which if you do that to 3, you get results that alternate between 2 and 4. Okay. But this sequence is not monotonic. It goes up and down. It oscillates between 2 and 4. So that first one is not monotonic. The second one is probably monotonic. It should probably just sort of, start off at 1. Yeah, it should probably start off at 1 and like tend towards 2. But so if you look at the terms of b sub n, for your first term you would plug in 1, and that gives you 2 over 2, which is 1. For your second term you plug in 2, that gives you 4 over 3. For your third term you would plug in 3, that gives you 6 over 4. Or, 3 halves or 1 1/2, whichever, whatever you want to say. And basically what's going to happen is the top is going to increase by 2's while the bottom increases by 1's because of the coefficients that are on these ends. So we'll get 8/5, 10/6, and you could simplify these. You don't have to though. I mean, it's easier to see what's going on when you don't simplify them. 12/7, and so on and so on. Now, these values do appear to be strictly increasing. Each one is at least as large as the previous one. So, you might venture a guess that this is monotonic because it's only increasing. And you'd be right. But if you really wanted to prove that it was monotonic, because you can't list out every term, there are infinitely many of them. You can't list out every term to prove that every term is at least as large as the one immediately before it. What you can do is compare the n plus 1th term to the nth term. And how you do that is, well, this is definitely, so the nth term is definitely 2n over 1 plus n. That's literally what it gives us that the nth term is. Whereas for the n plus 1th term, you just go everywhere where there's an n and plug in parentheses n plus 1. And sort of figure out that inequality from there. Let's see. So the n plus 1th term would be 2 times not n, but n plus 1. You just sort of substitute n plus 1 in everywhere where there's an n, over 1 plus, and instead of n plus 1. So this is, let's see, this is 2n plus 2. Over, that's going to simplify to n plus 2. And this is still 2n over 1 plus n. Okay. And, we don't know whether this is always less than, always less than or equal to, or always greater than or equal to. So we don't really know the relationship between these, but I mean, we have a sense that that the next terms are bigger than the previous ones. So why don't we just put a greater than symbol here, that the n plus 1th term is greater than the nth term, greater than or equal to. Okay. And we'll continue this somewhere where there's more, space. Now what you can do is, to simplify this inequality a little bit, you can multiply both sides by the least common denominator, which is to say, multiply both sides by both n plus 2 and n and 1 plus n. And this should cancel out the n plus 2 on the left and the 1 plus n on the right. And so what we end up with is 1 plus n times 2n plus 2, which, if you sort of follow that out, that ends up being 2n squared, okay, 2n plus 4n plus 2. And it's going to be, let's see, 2n, on the right-hand side, that's going to be 2n squared plus 4n. And you can just, you got a 2n squared and a 4n on both sides, so you can actually simplify that inequality to be 2 is greater than or equal to 0, which is true, which means that the whole, inequality this whole time has been true, that the n plus 1th term is indeed greater than or equal to the nth term. So it is monotonic, and because it's strictly increasing, the next term is always going to be bigger than the previous one. And then the last sequence, right? So if you wanted to prove the monotonicity of a sequence, sort of this is how you would do it. You would plug in n plus 1 into the formula for the nth term to get the n plus 1th term, and compare that in an inequality to, well, the nth term, which is just the formula itself, and eventually you'd be able to reduce it to some sort of inequality that you can say, okay, well, what this means is that, since we ended up with, for example, 2 is greater than or equal to 0, that means that the left-hand side was greater than the right-hand side all along. And you can prove that the n plus, the next term will always be bigger than the previous term, something like that. Now the last sequence, no, that's not right. Okay. N squared over 2n minus 1. If we write out the first couple of terms of that, that'll be the sequence where you plug in 1, that's going to be 1 on top over 2 minus 1, so 1. Okay. If you plug in 2, that's going to be 4 over 4 minus 1, so 4 over 3. Top is, if you plug in 3, top is going to be 9, bottom is going to be 7. Plug in 4, it's going to be 16 over 2 to the 4, 16 fifteenths. Okay. Now, if you were to go ahead and plot these, you would see that it is not monotonic. I know these fractions are sort of hard to compare to one another, but here's n, here's the value of c sub n, and let's just say that's 1 and that's 2. Okay, and then n is 1, 2, 3, 4, 5 or so. So with n being 1, we get 1, so we can sort of plot that term of the sequence right here. With n being 2, we get 4/3, which is about 1 1/3, or it is 1 1/3, so that's about here. And then 9/7 is 1 2/7. Which is less than 1 1/3. And then 16/15 is 1 1/16, which is definitely less than that. So that it has this sort of pattern of going up and then going down. It just goes up on the first term, and then it actually goes down thereafter. So this is not monotonic. If you were, though, somehow able to cut out the first term from that, and just consider the second term onwards, that sequence without the first term would be monotonic because it would be only decreasing. I guess the next term would be, what, 25/31, which is, even less than 1, so that would be, approximately 5/6. That would be somewhere here. All right, so monotonic just means moving in one direction only as opposed to both up and down. Maybe it moves, only down, or maybe it moves only up. So that's monotonicity. Now, boundedness is a property of sequences where you're basically saying the sequence never goes above this number, or the sequence never goes below this number. So a sequence is bounded above when there is a real number m such that a is less than m for all n. All that's saying is that a sequence is bounded above if all terms are less than some number. So if you have your sequence and all your terms, like all your infinitely many terms, are below 100, that sequence is bounded above by the number 100. It's also bounded above by the number 101 and 102 and 103.57. A sequence would be bounded above by any number that all of its terms are below. And the opposite is true for a sequence being bounded above. Bounded below. A sequence is bounded below if there's a number that it never goes, lower than. If there's some number that is lower than all the terms in the sequence. So if all terms are greater than some number that you can call n, say all your terms are, above 0, then your sequence is bounded below by the value 0. So that's what's meant by that's what's specifically meant by bounded above and bounded below. If it has both a lower bound and an upper bound, you just say it's bounded. But to be bounded, it has to have both. It has to be bounded both above and below to be bound. For you to just be able to call it bounded. Okay, so for example, for a sequence that's, bounded, let's think about the sequence, let's think about the sequence that goes, yeah, 0, 1/2, let's say 3/4, 7/8, 15 16ths, 31 30-seconds. Yeah. So here's the n-axis, and here's the values of the sequence. Okay, so we'll just have like 1 right here. Okay. So the first term is 0, meaning that for n equals 1, it's down here. Second term is 1/2, which means it's sort of halfway up to 1. 3/4 of the way up to 1 is sort of like half of the remaining distance. The next term is 7/8, so that's halfway of the remaining distance there. And let me draw this in to sort of assist me in the next term will be half of that remaining distance, basically, and so on and so on. And it never actually reaches 1. Although the terms of the sequence are definitely like approaching 1. But this 1, because it's above every term that's ever going to be in the sequence, 1 is an upper bound. For this sequence. And technically speaking, this also has a lower bound because these terms, they never go below 0. I mean, one of them is 0, but that's fine. And so, I guess I should say like greater than or equal, or like less than or equal. Okay. But technically speaking, 0 is also a lower bound. So this is a bounded sequence. All its terms are, all its terms like forever are going to be in between 0 and 1. So 1 is an upper bound, but so are 2 and 3 and 100 and 999,999. Those are all upper bounds because those are all numbers that the sequence is like completely below. And of course, there are other lower bounds as well. -1 is a lower bound, like the sequence never goes below -1. And -2 also, the sequence never goes below. Of course, if it doesn't go, if it's never less than 0, it's definitely not going to be less than -2 either. So -2 and -1 and -100 million, those are all lower bounds. If that seems like a lot of upper and lower bounds to be having, that's, you'd be correct. That's why usually there's only one particular upper bound or one particular lower bound under consideration, and that's called those are called the least upper bound, or the greatest lower bound, but that gets talked about a little less. Don't worry too much about this, but just know that there exists, there generally exists, if a sequence has upper bounds, that there is generally going to be a lowest one. So if we sort of look back at the sequence, there are a lot of upper bounds, right? And, there's 1, there's 2, there's 3, there's 100, there's 999,999. Those are all upper bounds. But the lowest that you can go while still being an upper bound is 1. Any lower than 1, even if you do like 0.999999, the sequence is gonna touch and go past that eventually. Just because it gets like so, infinitesimally close to 1. So 1 is the least upper bound out of all the upper bounds. So, just, although there are a lot of upper bounds out there, for this sequence, 1 is special. It is the lowest upper bound that the sequence has. If the value were any lower than that, even by like a little bit, it would cease to be an upper bound. So 1 is the lowest upper bound for this sequence. So we'll consider this sequence. Sequence that goes 1/2, 2/3, 3/4, 4/5, 5/7, all the way to like 99 100ths. 199 over 200, 1,000 over 1,001, a million over 1,000,001. Those numbers are always going to be less than 1. And of course, as you go, they're going to be less than 1 by increasingly smaller and smaller amounts, but they will all be less than 1. And 1 is the lowest number that all these terms are going to be less than. You can't do, 0.999, because eventually you're going to come up with a number that goes past 0.999. But you're never going to come up with a number in the sequence that goes past 1. And 1 is the lowest number for which that's true. So there are bounded sequences and unbounded sequences and monotonic sequences and non-monotonic sequences. Those properties are sort of like independent of each other. They don't necessarily, you can't just take it for granted that they're related. So for example, okay. There are sequences that are all sorts of combinations of these two properties. So don't like think that just because something is bounded it must be monotonic. So something that is bounded and monotonic. You might think that if something's monotonic, that it's only increasing, that it must just grow forever. But that's not the case. Something can be monotonic, that is increasing forever, but still be bounded. If it's increasing by less and less each time, you can maintain, it's this sort of increasing property while never actually growing past a certain value. So it is possible for a sequence to be both bounded and monotonic. An unbounded monotonic sequence, that's easy to think of. That would just be a sequence that just grows, forever. So that it's unbounded, and since it's only increasing, it's monotonic. You can have a function that's bounded and yet non-monotonic. That is to say, it goes up and down while being bounded. That would just be a function, that would just be a sequence kind of like our 2, 4, 2, 4. That would be like a sequence that goes like this. It never goes past these bounds, but it just continually goes up and down in between these bounds. And last, an unbounded and non-monotonic function. Probably not one that we see too much of, but something like that would be maybe something that starts at here, goes up, then goes down a little further than it was before, then goes up a little further than it was before. Something like this. And in truth, these sequences don't have like lines going in between the points, but just to sort of visually link each term to the next. So that would be unbounded because it just keeps growing, but it grows sort of like in both directions in sort of non-monotonic fashion. So all sorts of combinations of these properties can exist. But the one that we're going to be talking about right now is just sequences that are both bounded and monotonic. If you just sort of look at that sequence for a second, it's monotonic, so it's continually increasing, but it's also bounded, so it can't just increase to, infinity. It has to sort of be increasing by continually getting closer and closer to a particular value that it cannot go past because it's bounded. And because of this combination of properties, that it has to be monotonic, but also bounded, like it has to always be increasing, or possibly always decreasing, but also that it can't go past a particular value. It has to sort of approach that value very slowly. And so every bounded and monotonic sequence is convergent. In fact, it converges to the value of the bound that it's approaching. Because it must. I mean, how do you keep moving in one direction while still staying within, certain bounds? You must approach that bound, continually getting closer and closer to it, but never going past it. And so, if you wanted to prove that a sequence was convergent, but you didn't know how, one possibility might be, depending on what the sequence is, if you're able to prove that it's bounded and also prove that it's monotonic, automatically it's convergent. So, all right, so let's go back to this. What I just said was basically this. If a sequence is bounded and monotonic, then it converges. Yeah. Which is true of this. This is a bounded sequence. All the numbers, all the terms of the sequence are greater than 1/2. 1/2 is the lowest term that'll ever be in the sequence, and it's the first one. They're in between 1/2 and 1 because all these terms will be greater than 1/2, greater than or equal to 1/2, and they'll be less than 1. So it is bounded, and it is also monotonic because each term is greater than the previous one. And so this term, the sequence actually is a convergent sequence, and it converges to that upper bound of 1, which you could actually just sort of do, like find out by taking the limit of n over n plus 1 as n goes to infinity. You can actually find out it's convergent that way, but Okay. Okay, so sequence 1 over n is both bounded and monotonic. It's here. I'll write out the first couple of terms of that. 1 over 1 is 1. 1 over 2 is 1/2. Then 1/3. Then 1/4. Then 1/5. All these terms are going to be in between 1 and 0, so it's bounded. And it's monotonic because each term is less than the previous one, so this is a convergent sequence. It converges to 0. I mean, you sort of look at 1 over n, you can sort of see that the limit as n goes to infinity of these terms would be 0. The sequence n squared on top with n plus 1 on the bottom, it is monotonic in that all the terms are increasing, but it actually increases to infinity. It's not bounded above. Just it sort of goes past, greater than every number that you could possibly think of. It eventually surpasses, a value of 1 million. Then it surpasses 10 million as n gets large enough. So it's a divergent sequence. And -1 to the n, that's the sequence that just goes -1, 1, -1, 1, -1, 1. And, that is bounded. It's bounded by, 1 and -1. Like, it never goes past those bounds, but it's not monotonic. So you can't say anything about its convergence. And, in fact, this is a divergent sequence because it never actually settles upon any sort of value. All right, so that's sequences. Okay. Now we're going to go on to talk about what we're actually sort of, in this chapter to talk about, which is series. Okay. So we'll talk about what a series is. It's related to a sequence, but they're not like the same. And you don't want to get sort of tripped up over like the properties of series versus the properties of sequences because not everything is the same in between them. And we'll look at some simple examples of series and sort of get eased into the idea of there being tests for a series' convergence or divergence. So an infinite series is just an infinite sum. It's an infinite sum of the infinitely many terms of a sequence. So it's like a sequence, except instead of just listing out the terms, you are actually like, there are plus signs in between. You are adding them up into something. So the notation for a series is this sigma, which is just sort of the Greek letter that it's analogous to the Latin letter S, which we use for summation. And this down here is the index, sort of the same kind of index as you might see in, like, I don't know, computer science or something, to describe like your position in an array or something like that. But what this index means is that it tells you where n begins, and generally it's 1. Generally you start with n equals 1, but it is possible to start with n equals 0 or n equals 2. Just pay attention to that, and just remember that it might not always just automatically be starting at n equals 1. And this just represents the fact that wherever n starts, n goes to infinity. There are infinitely many terms in here that you're adding up. So this infinite sum of the terms of a sub n, that's just the first term plus the second term plus the third term plus the nth term plus just like all the terms from in this case starting from 1 to infinity. So it is possible. To like add infinitely many things together, but still come out with a finite sum. One example. One pretty standard example, that we've probably talked about before is, taking 1/2 and adding 1/4, and then adding 1/8, and then adding 1/16, then adding 1/32, basically adding, together the reciprocals of the powers of 2. And as long as you do this sort of forever, for infinitely many terms, this is eventually just going to equal 1. Each term gets you halfway of the rest of the way up to 1. So that if you do it, infinitely long, you reach 1 after infinity of these terms. So oftentimes these sums will equal a finite value, in which case we say that it converges. Sometimes they won't. Sometimes the sum will just grow to infinity the more and more terms you sort of pile onto it, in which case we say that it diverges. But one way to tell whether a series, one of these infinite sums, whether one of these series will equal a finite value or not, whether it will converge or diverge, is to consider the partial sums. So of course, the series itself is like infinitely many terms added together. But you can sort of get a start as to how that's going to go if you first consider just the first term, then just the first 2 terms, then just the first 3 terms, and so on. So that's why they call it partial sums, because the series is like the whole sum. But you start with just 1 term, and then maybe 2 terms, and then 3 terms. You take these partial sums as opposed to the whole infinite series. So you consider, so you make up basically a list of the partial sums, and you see where that list is sort of going to. The first partial sum is the first term. The second partial sum is the first and second term. The third partial sum are the first three terms. And so on and so on. If you make enough of these, sometimes you can start to sort of, suss out a pattern as to where these partial sums are going. Like what, as you add on more and more terms, are the partial sums getting closer and closer to some sort of value? And if so, then it's very likely that the entire infinite sum is that value that these partial sums are going to. And so the nth partial sum is, of course, the first n terms. So if these partial sums eventually go towards something, then the series converges. And we'll be making up lists of partial sums, and we'll you don't necessarily have to worry so much about remembering this definition. No one's going to ask you to define what the convergence of a series is, but just for an infinite series, right, where you're adding up all the terms a sub n, the partial sum, the nth partial sum is just you take the first n terms and you add them together. Right, so you take the first 1 terms, you take the first 2 terms, you take the first 3 terms, and the first 4 terms, and so on, increasing the number of terms every time. And if those partial sums converge to a value, if as you take more and more terms and add them on, your partial sum sort of goes towards a particular finite value, then the series is said to converge. And whatever that value that the partial sums were going to, that is the sum of the series. If your partial sums, instead just start growing wildly, like, to infinity or something, then the series diverges instead. So if as you take more and more terms of a series, and add them together, you go towards a singular finite value, that's convergent. And otherwise, if anything else happens, the series is divergent. Right, so first we're going to consider that same sequence, that same series. Series is not a sequence. Okay. Now, of course, we know for some reason or another that this is 1. But we can look at the partial sums to really show why that is. So we'll form the first partial sum from the first term only. And the second partial sum from the first 2 terms. And the third partial sum from the first 3 terms. And we can keep doing this for a while, but it's probably good to stop after 4. And then eventually we'll come across maybe a formula for the nth partial sum. Okay, now the value of these partial sums is 1/2 is, 1/2. Half plus, shit, I forgot to put the 1/16 on here. Okay, so 1/2 is just 1/2. A half and a fourth, together that makes 3/4. A half and a fourth and an eighth, together, if you wanted to get those over common denominator, you could, but that's 7/8. Whereas a half plus a fourth plus an eighth plus a 16th is 15/16. So it appears that as we tack on, more and more terms, that the sum is sort of, like approaching some kind of value. And if you look at these partial sums that you've sort of been making, 1/2, 3/4, 7/8, 15/16, you might start to see a sort of pattern, and this is sort of where that pattern recognition is important. The denominators are just the powers of 2. 2, 4, 8, 16. So the denominators are the powers of 2. So just 2 to, and if you sort of pay attention to what n is at the time, for the fourth partial sum, the denominator is 16. The third partial sum, the denominator is 8. You might realize that you can write the denominators as 2 to the power of whatever n is. Now the numerators, 1, 3, 7, and 15, they might not seem to have a lot in common, but they are all actually one fewer than a power of 2. 1 is 1 less than 2, 3 is 1 less than 4, 7 is 1 less than 8. Or you can also think of it as it's the denominator minus 1. Either way, you come up with the fact that the numerator is expressed as 2 to the power of n, with a minus 1 sort of coming after it. Okay, so the partial sums can be made up this way. So if you wanted to find, say, like the 10th partial sum, you don't actually have to plug in 10 of these terms. Once you form this formula for the nth partial sum, you can just say, okay, well, I'm looking for the 10th partial sum, so I should plug in 10 here, and you would get, 1023 over 1024, which is, and these are rapidly getting, well, not rapidly, but like these are getting closer and closer and closer to a value of 1. So the limit of these partial sums, that is, as you take more and more terms, as you go on to, take the first 100 terms, or take the first 1,000 terms, or take the first 1,000,000 terms, the limit of this, limit of these partial sums is 1. That is, the more and more terms you tack on, even up to infinitely many terms, the closer and closer you get to 1. So 1 is the sum of this series. Okay, so that's one way. That's one way to sort of check for the convergence or divergence of a series, is sort of like this direct way where you literally take the terms and start adding them together and see where that sort of takes you. And in this case, it takes us to 1. Although there are certainly like other potentially simpler tests for convergence or divergence, depending on what the series is, but this is definitely sort of the most elementary. Like literally start adding the terms together, and see where that sum goes as you tack on more and more terms. here is a series where it's a series where each term of the series is actually made up of like two terms, or like two separate things. So that this here is the first term. This here is the second term. This is the third term. And we'll form the partial sums of these as well. Okay, so the first partial sum is just going to be the first term, of course. So that's going to be 1 minus 1/2. And we'll just sort of leave it looking like that for now. The second partial sum would be the first two of these terms of the series. So that's 1 minus 1/2, that's the first term, plus 1/2 minus 1/3. Now you might sort of see what's going to happen here. This minus 1/2 is going to cancel out with this plus 1/2. Just sort of eventually when you actually smush them together, and you're going to be left with the one that's in the front and the minus 1/3 that's in the back. The third partial sum is going to be the three terms that we see here. And the same thing's going to happen with the 1/2s. But it's also going to happen with these 1/3s now, with the inclusion of the third term here. The minus 1/2 will cancel out with the plus 1/2, but the minus 1/3 will cancel out with the plus 1/3. So that we're just left with, again, the 1 from the beginning, and then the minus 1/4 at the end. And so you can sort of imagine this happening over and over the more terms that you put, is that these middle terms are going to cancel each other out every time. And what you'll be left with is the one part of the first term that was that was there in the beginning, just that one that's in the front there, and the second part of whatever term is at the end. So just that last bit, that minus 1/4, or for the next one it'd be minus 1/5. The one after that would be minus 1/6. That would be left over at the end. So it looks like you can write the nth partial sum as always being that one that's in the front that pretty much never gets canceled out, minus 1 over, while it might be tempting to write 1 over n, just keep in mind that for the first partial sum, that number on the bottom was 2. For the second partial sum, that number on the bottom was 3. For the third partial sum, that number on the bottom was 4. So the bottom is actually expressed as n plus 1. That bottom of that number that you're subtracting from 1. Now, considering that nth partial sum, that is like, if you add 100 terms together, what you'll end up with is 1 minus 1 over 101. The limit of that, as n goes to infinity, that is, as you add up more and more terms, as n goes to infinity, this denominator here is going to grow, which means that this thing that's being subtracted away is going to shrink. Since you're dividing by something that's growing, so that thing is shrinking, and 1 minus this thing that's shrinking to 0, that limit is going to be 1. So the limit of this, so this series actually also equals 1. And it equals 1, like because of that 1 that's there in the beginning. Everything that comes after it eventually either gets canceled out, or in the case of the very last thing, shrinks to like nothing the more and more terms there are. And for the sort of last series that we're going to look at the partial sums of, that's going to be a divergent series. So if we just consider the series the infinite sum from n equals 1 to infinity of 1, meaning that just every term is 1 and we're doing that infinitely many times, if we add infinitely many 1's together, of course, it's going to be infinity. So even though, of course, even though the terms themselves are all just 1, because you're adding infinitely many of them together, this is a divergent series. But you can tell that by looking at the partial sums. So the first partial sum is 1. The second partial sum will be 1 plus 1. The third partial sum will, of course, be 1 plus 1 plus 1. So that you can probably deduce that the nth partial sum is literally just n. I mean, if each term is a 1, and you add n of those 1's together, it's going to make n. But the limit of this, as n goes to infinity, is infinity. So this is a divergent series. Yeah. The terms aren't growing, right? The terms are all just 1. So like even though the individual terms, you can say they're, you might say that the terms converge to 1. But even though the terms themselves are convergent, the process of adding them all up, the series that has you adding all those terms up, is divergent. All right, so the one that we just looked at previous to this, sort of 1 minus 1/2, plus 1/2 minus 1/3 plus 1/3 minus 1/4. That's known as a telescoping series. Because, with the way that it acts, where you sort of, cancel out all the middle terms and you're left with the first, the first part of the first term and like the very last part of whatever last term you have, that it behaves kind of like a telescope, that you can take a telescope like this, and sort of collapse it so that, I've also actually never seen a telescope. You can collapse it so that like basically only the first and last parts remain. So that these sort of all like, collapse or like nest into each other, all except for the very first part and the very last part. And so if you see a telescoping series like this, and and you'll be able to tell a telescoping series because each term is going to have like one, positive part and one negative part, and like the parts that are in, some parts that are in one term will appear again later in another term eventually. probably the best way to deal with those is to write out the first couple of partial sums, see what cancels out and see what doesn't. Generally speaking, with these, there might be one thing or a couple of things in the beginning that never get canceled out. And generally speaking, whatever's left over at the end, that's going to be shrinking to zero, so that basically you only have to ever think about the stuff that sort of occurs in the beginning and is never canceled out. So like the this part will generally speaking will shrink to zero, whereas this part will just remain there always and never get canceled out. So that this that again this series equals 1. Of course, for that to happen, this part that is there at the end has to eventually shrink to 0. I mean, I guess it doesn't shrink to 0. It has to, the part that's left over at the end has to converge to a finite number. Maybe it converges to 0, like it did for the one that we saw. Maybe it converges to 1, but as long as it converges to something finite, we sort of look at this. If we just sort of looked at this last term and just maybe imagine that hypothetically it converges, whatever the last term is converges to like -1 or something. Then eventually, after taking a bunch of terms, it would just start to become 1 minus 1, and it would be 0 if that last term converged to -1. So the condition for the convergence of a telescoping series like this is just that whatever the last bit is at the end is something finite, as opposed to something that just keeps growing to infinity. But, of course, still the best way is to probably write out the first couple of terms, see what gets canceled out, with every term that you add on, and see what is sort of left over at the end and what that thing that's left over at the end is doing. Okay, so a geometric series is a type of series that is called what it is because each term is in a constant ratio to the previous term. So again, this series where you have 1/2, and then you add 1/4, and then you add 1/8, and then you add 1/16. That's a geometric series because each term is 1/2 of the previous term. Any series where this happens, each term that you're adding on being a particular ratio to the previous term, that is a geometric series, and it can be written this way. The infinite sum from n equals 0, it doesn't have to start at n equals 0. It can start at n equals 1, and in that case, you'll just have one fewer term in the beginning. But it equals, whatever a is, if a is even anything at all, maybe a is just 1 and you don't have to think about it at all. That each term is just, basically increasing powers of something. But that thing that's getting taken to that nth power is the ratio. So, for example, this series is simply the infinite series from 1 to infinity of, I mean, if you want it there, you can have a 1 in the front, but it's 1 times the ratio 1/2 to the nth power. And it's just written this way because 1 to any power is 1. And then 2 to the nth power down here will be 2 to the n. But this here is the ratio. Whatever is getting taken to the nth power is the ratio. So there's an easy way to tell whether a geometric series converges or diverges. And that's just going to be based on what the ratio is. Okay. If the ratio is in between -1 and 1, basically, the ratio can be negative, that's fine. But as long as its absolute value is less than 1, it's going to converge. If the absolute value of the ratio is greater than or equal to 1, it will diverge instead. And the reason for that is if you have a ratio that's less than 1, so for example, like if you have a ratio of, 0.999, that's less than 1, and you take something that's less than 1 and raise it to particularly high power, and you just sort of keep doing that for higher and higher powers. Let's take that to the 100th power. They will eventually shrink. I probably should have picked something else. Okay. Let's just do 0.9. Okay. Let's just do 0.9 to the 10 first. And so starting with a ratio less than 1 and taking that to increasing powers is just going to create smaller and smaller numbers that we're sort of adding together, but at least the things we're adding together are, getting smaller and smaller. Where the 20th term is just 0.1 to, and eventually they'll all shrink to where they're just sort of vanishingly small. Whereas if we start with something that's greater than 1, a ratio that's greater than 1, and we exponentiate that, I mean, taking something that's greater than 1 and putting it to a power will obviously cause it to increase as opposed to decrease. So that, I don't know, let's start with the 10th power. That's already 2.6, if we take it to an even higher power, it's 2.8. And so, if the ratio is greater than 1, your terms are actually, the terms that you're adding together are literally growing. Each term is going to be bigger than the last one that you're adding together. And so, of course, that would cause a series to diverge if you're adding together increasingly larger numbers as you go. So just if the ratio is in between -1 and 1, a geometric series will converge. And of course, if the ratio is in between -1 and 1, or you can also say that the absolute value of r is less than 1, then the series converges. If the absolute value of r is greater than 1, then the series diverges. And not only can you know that it converges or diverges, you can know that whenever it converges, you can know exactly what value that the sum converges to. And that, that can be given by this formula, but an easier easier way is like, so if a geometric series converges, which is to say, its ratio is less than, the absolute value of the ratio is less than 1. Like the ratio is in between -1 and 1. What it equals is just whatever the first term is. See, this way, this sort of depends on n starting at 0. But if you just sort of put whatever the first term is on top, and put that over 1 minus r, then you won't have to worry about whether you're starting at 0 or starting at 1 or starting at n equals 2. It's just whatever term you have first on top, divided by 1 over the ratio. So this thing right here, we know this converges to 1, but if you say, took this to where the first term was on top, so 1/2 over 1 minus the ratio of 1/2. That's 1/2 over 1/2, which is 1, which is the sum of the series. Okay, so we'll test a couple of geometric series for their convergence or divergence. You know what? Let's take even less than that. Let's just take this. Right. So the infinite sum, starting at 0, going to infinity, of 3 over 2 to the n. Now that 3 is not to the n power. So that's not part of, that 3 is not part of the ratio. It's not being raised to the n power. So what you can do is you can sort of bring it out to the front and sort of separate it out a little bit. So n equals 0 to infinity of just 3 in front of 1/2, like 1 over 2 being raised to the n power. So this here is the ratio. And that 3 is just some sort of coefficient that just gets multiplied in there. But the 3 doesn't get raised to the n power, so it's not part of the ratio. Okay, so this infinite series is going to start, and it is a sum, so we don't need, it's not a list of numbers. We're not putting these in curly braces. The first term of this series, with n starting at 0, if you sort of plug 0 in for n here, well, anything to the 0 power is 1. So the first term is going to be 3. Plus, 3 times 1/2, plus 3 times 1/4, plus 3 times 1/8, and so on. Although you only really need the first term. Now this series is going to converge, because the ratio is in between -1 and 1. Like the absolute value of the ratio is, the absolute value of 1/2 is less than 1. So that converges. the 3 doesn't matter in terms of like its convergence. It's the ratio being less than 1 that causes the things you're adding together to shrink, these terms to shrink enough for the infinite sum to sort of close in on a value as opposed to growing infinitely. And in addition, you can say that it converges. Since you know that it converges, you can say that this geometric series will converge to a particular value. And it'll just converge to that first term, 3, over 1 minus the ratio of 1/2. So that's 3 over 1 minus 1/2 is 1/2. 3 divided by 1/2 is 3 times 2, which is 6. And you can sort of see that behavior here. Just if you, I don't know, start with 3, add 3 halves. Add 3/4, add 3/8 to that, add 3/16 to that. Then you add 3/64, I guess, and 3/128. That this sort of sum where you keep adding these terms together is sort of closing in on a value of 6. We're not actually going to calculate very much of this. A different geometric series with the ratio of 3 halves, which means that each successive term is 3 halves or 1.5 times the previous one, so that the terms are actually growing the more of them you add. Each term is bigger than the previous one. That's going to diverge, and that has to do with the fact that its ratio is greater than 1, causing the terms that you're adding together to grow rather than to shrink, which just means the more of them you add up, the greater and greater your sum is going to be, and that sum is going to diverge to infinity, since that ratio is greater than 1. So we've seen a couple of convergent series that we've been able to say like equals a number. So for example, we've seen the infinite sum of 1/2 to the nth power with n starting at 1. Like we've been able to say that equals 1. That's the sum where you take 1/2, you add a 4th, you add an 8th, you add a 16th. We've been able to say that is 1. Or the one that we just saw, 3 over 2 to the n is sort of how it started, with n starting at 0 and going to infinity. We found out just now that is equal to 6. So convergent series, like they have values, like they have numerical values, and what that means for convergent series is, since they have numerical values, you can treat them just like numbers. You can manipulate them like with each other just like numbers. So you don't actually have to write this down, but just sort of, it's kind of intuitive is what it is. So as long as they're convergent, because if they were divergent, they'd be like infinity or something. But as long as they're convergent, which means they are numbers, basically, they equal out to numbers. If one convergent series equals a number A and a different convergent series equals a number B, then making up a series out of the two series added together, that's going to equal their sums added together. If you make up a new series from the two series being subtracted, the sum of that will be the two previous sums subtracted in the same way. Basically, since these series are equal to numbers, they just work the same way, like as numbers. And also, if you take a number and you multiply it by a constant, of course the result will just be the constant times that number. So if you have a convergent series and you multiply by 3, the sum of the new series that you make by multiplying a series by 3, it'll just be 3 times the old sum. So this is just to say that you can do scalar multiplication on series, you can add series together, their sum will be the old sums added together, and you can subtract series too. Their sum will just be the old sums subtracted one from the other. And this is all if they're convergent. They both have to be convergent, because if either one of the series is divergent, they more or less act like infinity or something, and that messes the whole thing up. But as long as they're both convergent, they behave just the same way as the numbers that they, really equal. Okay. We'll talk about this last part on Tuesday.